Hello. In the second video of the series, we learn about equivalent capacitance. So we will have a network of capacitors connected in series or connected in parallel, and we'd like to replace them with one equivalent capacitor. So as a reminder, capacitor is a dynamic element that saves energy in form of electric charge, and we studied the voltage-current relationship as follows. The current through the capacitor is proportional to the derivative of the voltage across the capacitor, and if we integrate this equation, the voltage over the capacitor is equal to the integral of the current through the capacitor times 1 over C, where C is the capacitance of our capacitor. Now we start with a series circuit. So let's assume here that I have a voltage source, Vt, supplying a current I. In the series network, I have C1 in series to C2, and I'd like to get an equivalent capacitance such that an equivalent circuit to the one on the left hand side can be shown as follows. I have my supply Vt supplying a current I, and I'd like to replace these two capacitors with one equivalent capacitor. Let's call it here Ct. So far so good. Now I'd like to study the relationship between Vt and I in terms of C. Since the capacitor is in parallel to the supply source, the voltage across the capacitor V is equal to Vt, and the current through the capacitor is the same as the supply current. So as a result, I can give an expression for the capacitor voltage, Vc of t, which is the same as the supply voltage, Vt. This is equal to 1 over C integral of I dt, using the physics of the capacitor. Okay, so now I have a relationship between the supply voltage, supply current, and the equivalent capacitor that I wish. Let's do analyses on the circuit on the left hand side to see how can I combine C1 and C2 such that I use this equation here. So to start, we have the circuit on the left. I have my power supply Vt. How about we write a KVL here? So writing a KVL would give us Vt equal to V1 and V2, given that V1 is the voltage across capacitor 1 and V2 is the voltage across capacitor 2. I'm going to replace Vt using the equations that we derived in the previous slide, this one. So it has the total capacitance, it has I, so I have it here. Now I can write the voltage across capacitor 1 and the voltage across capacitor 2 in terms of the current in each. But since both are in series, they share the same current. And since this is the series network, the current going through the two capacitors is the same as I, the current supplied from our source. So I have it here. So V1 would be the integral of I dt over C1, and V2 is the integral of I dt over C2. Now, for this equality to hold, we must have 1 over Ct equal to 1 over C1 plus C2. So from there, I can give you an expression for the equivalent capacitance, Ct equals to C1 C2 over C1 plus C2. If you notice, this equation looks like as if we are combining parallel resistors. So capacitors in series would follow an equation that looks like a parallel resistor. So in general, if I have more than two capacitors in series, 1 over the equivalent capacitance is equal to a summation of the inverse capacitance of all of my capacitors. Now let's move to a parallel combination. So assume here that I have two parallel capacitors and I'd like to replace them with one equivalent capacitor. So for the circuit, let's assume that I have a current source Is or It that supply this network. And since all three elements here are in parallel, so they have the same voltage V across all of them, I'd like to replace the circuit with one equivalent circuit that has my source It, and I replace the parallel combination with one equivalent capacitor Ct. And again, since they are parallel, they have the same voltage drop. And here's the current going through CT as IT because the two elements here making a series network. Okay, so I can write an expression for IT in terms of the capacitor because IT is now the current going through the capacitor CT. So IT can be written as CT dV dt. Now let me take this equation, keep it in mind, and go back to the original circuit on the left. Okay, so here we have our current source IT. Okay, so here I have a node. The current input is IT. I have two current outputs, I1 and I2, so I can write this KCL equation. IT is entering the node, I1 and I2 are leaving. I have an expression for IT from the previous slide in terms of the equivalent capacitance from here. And then I can represent I1 and I2 using the capacitance and the voltage across capacitor 1 and voltage across capacitor 2. But when you look at the circuit, all three elements are in parallel, so they have the same voltage V. So the current I1 can be represented as C1 dV1 dt, but V1 is the same as V, and V2 is the same as V. So I2 is equal to C2 dV dt. Now for this equation to hold, we should have CT equal to C1 plus C2, because this right hand side here can be written as C1 plus C2 times dV dt, and the left hand side is CT dV dt. So for equality, these two terms has to equal each other, so the equivalent capacitance would equal to C1 plus C2. So if we have two parallel capacitors, I can replace them with one equivalent capacitor whose value is the summation of the two capacitances. In general, the equivalent capacitance of n parallel capacitor would be simply the summation of all these capacitances. Let's apply an example for that. So here I have a network of capacitors and I'd like to get the equivalent capacitance CT. So first of all, you can see that these two here are in series, so I can replace them by one equivalent capacitor. Let me call it CS. So my circuit will become C1, and then I replace C2 and C3 by one equivalent capacitance. Let's call it CS, where CS is the series combination of C2 and C3. When we do series combination, we treat them as if they are parallel resistors, so we do multiplication over the summation, and this gives us 150 picofarad. Now, to still get the equivalent capacitance, I have C1 in parallel to CS. We reduce parallel capacitors by adding them together, so CT would be C1 parallel to CS. When we do the parallel, we add them together here. So the equivalent capacitance is equal to 3.65 nanofarad. So to recap, in this video we learned about the series combination of capacitor and the parallel combination. The equivalent capacitance for a series combination follow this equation. 1 over CT is equal to 1 over C1 plus 1 over C2 plus if I have more than 2. Specifically, if I have exactly 2 series capacitors, the equivalent capacitance CT would be the multiplication of both divided over the summation. For parallel capacitors, I can replace them with one equivalent capacitor whose value is the summation of those parallel capacitors. And this concludes this video. Thank you so much for listening.